In this video, we're going to look at the number of fish required for colonization, and we'll examine how we can estimate the probability of colonization. So we looked before at the number of fish that can pass through the system per year, and just to review that, we looked at the year T0. We could look at the number of fish that would pass through from year T1 through year T10, and there's a sum there. I'm in the small population column here. Then we could say, well, given that we haven't had establishment by year T10, what happens? And we have the number of fish per year from T11 through T50 and a sum. And the same thing is true for the medium population and the large population. So that's just by way of review. Because this number here, these sums, 3 that we see in the current screenshot, are going to be important to us. And this is the value that we're going to focus on right now. This value here is a critical value that would be elicited from our experts. And what we would ask is, what is the smallest number of fish that must get through the system by year T0 to convince you they will colonize? What is the smallest number of fish that must get through the system by year T0 to convince you they will colonize? And so our expert here, again, the hypothetical expert, said, well, I read the Cuddington article, and that said it could be as few as 20 fish. That seems kind of low, but let's go with 20 as a minimum. And this expert says, if 500 fish get through in 6 years' time, I'm sure there will be colonization. And then we elicit these other values. There's a 25% chance that it could happen with 40 or less, and a 75% chance that it would happen with 250 or less. Over here, we have the same distribution. The number of fish required for colonization by year T0 is the same no matter what the size of the population is. So this is the same 20, 40, 250, 500 that we looked at before, as is this. 20, 40, 250, 500. When we get down here, the number of fish required for colonization by year T10, we would have a different number. So instead of 20, 40, 250, and 500, you see our expert estimated a different number of fish. So here's how we use this. We don't know the number of fish required for colonization. That's an uncertain value. But our experts have helped to characterize the uncertainty here. So when I hit F9, you can see different possible thresholds. So what we do is we take the number, the sum of fish that actually get through in the 6 years leading up to time T0, and compare that to the number of fish required for colonization. If this number here, the sum, is bigger than this number here, the number of fish required, then over here we have colonization, yes or no. A 0 means no, we did not have colonization in this circumstance. Let's take a look at the medium population iteration here. Here we had 54 fish getting through, and here we were saying, well, what if 29 are required? Then the answer is a 1. We would have colonization. And if we take a look at the numbers here for the large population, 111 fish get through, but this says, what if 131 are required? Then once again we'd say, well, then there is no colonization. So we can iterate this. You see the numbers changing here. Let me stop here. This is the circumstance where we had 36 fish get through. 30 of them are required for colonization, so this is a 1. We do have colonization. 63 is less than 241, so we have a 0 here. 117 is bigger than 59, so we have a 1 here. What we do, let me just set this to 100 so it goes quickly, is we would do a simulation here of 1,000 or 10,000 different iterations. And it's going to save these zeros and ones. So we did 100. You'll notice over here that the minimum value obtained was a 0, the maximum was a 1, as expected. And the mean, if you add up all 100 numbers and divide by 100, we had a 0.07. So this is basically saying we got 7 instances of colonization. So the probability of colonization given a small population arrives is 0.07 based on this brief simulation. Over here, we would see that there were 33 instances of colonization when we had a medium population pushing the fish through. So there would be a 33% chance of colonization. And if we look at the final number, we see with the large population pushing, there were 45 instances of colonization. So the probability is 0.45. Now, prior to making this video, I ran a simulation of 1,000 iterations, and these will be the results, and you'll see those results in each of the shaded areas that I have here. So let's focus on this one here. When I did the original run, there was a 0.106 chance of colonization. 1 minus p is 0.894, as you see here. My sample size was 1,000 when I did that. I calculate the standard error of the population proportion. That's a very simple calculation. You can see it up here in the formula bar if you're interested. This standard error and this estimate of the proportion, together with the sample size, tell me that the sampling distribution is a normal distribution. It has a mean of 0.106 and a standard deviation of 0.009. So now I have a distribution. Even though we calculated a single number, we can calculate the sampling distribution for it, estimate the sampling distribution, and that is right here. So this would be my way of estimating the probability of colonization by year T0 with a small population pushing fish through. In a similar fashion, I have developed a distribution for the medium-sized population and a distribution for the large-sized population. And if I was to scroll down the model, you would see this was done for year T10 also, and then for year T50. So what this gives me is a distribution that captures some of the uncertainty about the true value of this probability here. Okay? In the next video, I'm going to show you how we combine all that to come up with this probability of colonization here, and then we will complete the calculation.